In Moodle, basically, you have also this paper, which is basically a very nice paper about, as paper, basically it's a book, you can call it a book chapter that talks about kinematics, mainly forward and inverse kinematics, with some examples. So I recommend to read it. Basically, what I want to jump to is basically the forward kinematics session and to this example first, which shows again the DH2 here, conventions basically, or model. And what is important to consider there, this representation, because this would be important for the inverse kinematic. The idea there is that we have the transformation from base to end effector. As I said, DH2 starts from basically the transformation from, for example, I to I plus 1, or from I minus 1 to I, and so on until you reach the end effector. So this is from 0 to 1, 1 to 2, and so on. And when we do this multiplication, we get this transformation matrix, and what you see here, these notations or these symbols that represent, of course, models. So this basically would be what is represented by R here. They are rotational models. What we see here by X, Y, Z, they are basically the positional, or the position vector actually of the end effector point. Now, if we look here at the example, and this is basically a 6 degrees of freedom standard manipulator, and it's called the Stanford manipulator, sorry. So this is basically developed by Stanford University. What is interesting about this robot arm is that it has translation, or it has a prism joint, which basically here it has D3. This is the control parameter for the prism joint. Now, if we look here, basically, as in this example, we see the DH parameters table that we need to specify, and I will basically try together with you now look at these parameters and how they are derived. So we have first the x0, z0, y0, and we have the theta 1, which is always the shoulder rotation, and we have x1, z1, y1. Now we have the first rotational, which is here, they put theta in the beginning, and theta is always the rotation around z-axis. Okay, so the rotation here, which is represented by theta 1, is the rotation, if we look back at our slide basically. So we look at here, which is DH2. So it's the angle from positive xi to positive, so the angle between the two axes basically, and the angle is, or the rotation is around zi. So if I go back here, so basically this is the rotation around z1, and it is the theta, because this theta, if it rotates, it will create an angle between x0 and x1, the positive x0 and x1 around z1. Or actually, if we are rotating around z1, but here z1 or z0 are the same because they are on the same axis. Now we have alpha, which is basically usually the distance between the two z-axis if we are looking from x1 or x0, here the same because they are parallel. So z1 and z0, they are on the same axis, so they have no distance or no displacement between them. We have the this is the A, and this alpha is the rotation, so it's basically the displacement. This is the second rotation, which is the rotation around the x-axis in this case, and basically, or mainly, is a rotation around x, in this case is x0, and basically that creates an angle between z0 and z1. Now this is 0 and there is 1, and there is no rotation around x. There is no, this degree of freedom doesn't exist, right? So this is why it is 0. The last parameter that exists here, which is doing the transformation, or it is actually playing a part in the transformation from z to 1, is the h1, which is the distance between x0 and x1, and basically, and here along z1. Okay, so the distance between x0 and x1, which is h1. Now the next transformation, which is basically is between the first coordinate system and the second coordinate system. And here we have x1, z1, y1, and x2, z2, y2. We basically, if we look here, we have, of course, rotation and translation. And the first thing is we have theta 2, which is actually denoted here or represented here. And this is basically the rotation around z2, and basically with respect to this joint. So here we have a joint, and this joint doing this rotation, and theta 2 is the rotation around z2 that creates an angle between x1 and x2. Okay, so if I do this rotation, x2 would have an angle with x1. We have the second rotation, which is alpha, which is here rotation around x, basically 1 here in this case, so x1. That creates an angle between the two z axes. Now if we look here, this is z1 and this is z2, there is an angle between them. There is a fixed angle, and this basically angle is 90 degree, and basically it's 90 because the positive is the counterclockwise, and this is basically the positive direction, right? So this is z1 and z2, and z2 actually, if we consider before rotation, was aligned with z1, and then after rotation, if we go counterclockwise, it would be in this direction. This is why we have it here as a 19. Now there is no translation there basically between z1 and z2 if I'm looking from the x direction, because they are on the same plane. There is translation between, of course, x1 and x2 along z2, which is here is the d2, which is the links of that link basically. Now the next here is from 2 to 3, which is here it's a bit maybe ambiguous or not clear, because 3 is a prism joint. So 3 here is set as this link, and basically as a point that is translating along this axis. Now here, because we have prism, we have only 1 degree of freedom, which is a translation. Theta here is not a control parameter, but d3 is a control parameter, which is d is basically the translation along the z-axis. Now what we look here is that this is z3, and this is basically what we see there. So theta actually is 0 because there is no angle, or actually the angle between x2 and x3 is 0 because they are parallel. And this doesn't change because theta is not a variable here, theta is fixed, and this will always be 0 because this basically the two axes of the prism, or the two links of the prism, they are always at the same angle, of course, because they are to the prism, so there's no rotation. And this is basically why x3 and x2, they are always in parallel. Now we have basically we have the first here rotation, which is minus 90 degree, which is between z3 and x2. So here we started from x2 and we did the rotation around x3, and basically here minus 90 because it is in clockwise, so it's not, so the counterclockwise is positive, so clockwise is 90, so it's minus 90. Then there is no translation, which is basically it. So here we have the d3, which is the distance between the two x-axes, but between the z2 and z3, they are on the same plane. There is no translation. This is why it is 0, and d3 is our control parameter in this case. So this is given, and these are static, h1 and d2, but d3 is a control, so this is basically given by the actuator. Now we have 3 and 4. This is basically the point 4, and this is the point 3, or the coordinate 4 and point 3. There is no, you can see it's all zeros. There is only one rotation, which is basically around z4. which is this rotation that we see with theta 4 here. This is very similar to the first rotation that we have, which is the base, because here you can see that Z3 and Z4, they are aligned like Z0 and Z1, and we have this rotation. Now we continue like with actually now something like this one. So we have now rotation around Z, because now we have, whenever I have rotational joint, then I need to have theta. Otherwise theta would be fixed, either 0 or 90, or I don't know, it would be fixed. And here basically we have now theta 5, and basically that represents the rotation around joint 5, this one, and this is basically theta 6. Now if I go here, and if you basically just 1 second, I want to Stanford manipulator in action. So basically if we go to videos, just to understand how is this moving. So we see basically this rotation. We see that we have here the shoulder, we have the second rotation, we have here rotation, and this is the prism. We do have another rotation that is similar to the shoulder there. Then we have here rotation, and we have here rotation as well. So this is basically high degree of freedom robot arm. This is basically why we have 6 degrees of freedom. And this is basically the 5 and 6 degrees of freedom that we see there. So if we do this now, we have these parameters. We need to replace what we have here, which is the DH2 matrix. And this is C is representing cosine and S sine, just to simplify it. So here we see the transformation matrices, and what is done is that we have the multiplications, and these are the models, as I said, and this is basically the last 3 are the positional models of the end effector with respect to the reference or with respect to the base. And you can see that theta 1, theta 2, of course, they have played a role there, and we have D3, but basically in total this is the positional and this is the rotational of basically the end effector reference point. So if the reference point is only translating, which means I am not doing rotation, then the mere control parameters are theta 1, theta 2, and D2, or actually D3, because D2 and H1 are fixed, but D3, these are the main control parameters that are controlling the translation of the end effector point. But the end effector point also could rotate, which means this, which is the number 6, could rotate around basically different rotations, and these different rotations control are done here in the rotational part, which is this part. Okay, so this just for the inverse kinematic would be important later. If we look here, we know that if there's only translation, then basically usually the translation is always here in the last column of the homogeneous transformation, and we can see that is controlled by theta 1, theta 2, and D3 mainly. So theta 1, theta 2, and D3, they control the position translation of that point along X, Y, or Z, but if there is rotation, that would be done by the other joints. Okay, so thank you for this part. Next part to talk about the inverse kinematic, and if you have any question, as I said, either ask it today or tomorrow in the session of questions, or if you have any basically other questions, just send me an email and I either answer in the email or we can have a call as well for that. Thank you.